This entire system is running as a closed environment. Once it's shut, there's no airflow from the room and no pumps or filters correcting what's happening inside. The ecosystems have to entirely regulate themselves through the food web and the energy moving through the system. It's been 20 days since I closed the system, and that's long enough for patterns to start emerging. Nothing too dramatic, thankfully, but there are subtle signs that tell me whether the design is actually doing what it's supposed to be doing. Right now, humidity is lingering on the glass longer than I expected. Water is collecting in the atmosphere as it should be, but not at the rate the system was designed for. In a setup like this, those details are really important because condensation and temperature gradients are what drive the entire water cycle, so this design is working, but it's not entirely at its best. But before I go off and redesign the atmosphere or add any more complexity, I need to answer one specific question, and that is, does insulating the atmosphere actually improve efficiency, or is it a change that sounds important but ends up barely affecting how the system behaves? So in this video, I'm isolating that one variable. I'm insulating a single atmosphere, measuring temperature and humidity from the inside, and comparing it directly against other atmospheres running uninsulated. The goal is to find out whether insulation will meaningfully change performance, because the answer will determine how everything else gets built from here on out. For this test, I'm not trying to build a finished solution, so I'm not worried about how it looks at this point. What I want is an answer, and I want it as quickly and as cleanly as possible. Insulation is one of those changes that's easy to assume will help, but unless you actually test it in the system you're working with, you don't really know how much it matters. So the goal here is to get the most information with the least amount of disruption. To start off with, I'm using an inexpensive expanded polystyrene board, basically the same material some coolers are made out of. These can get really messy, and although there are much easier foams to work with, these polystyrene boards have good performance and they are the least expensive for this test. So to start off with, I'm insulating the bottom of the atmosphere first. The reason for this is that that part of the atmosphere gets the most amount of heat from the lights below, and I want to see if there can be some kind of boost in performance by insulating this bottom area. And so I press fit those pieces into place and I let the system run overnight. When I checked the conditions the next day, there wasn't a noticeable change compared to the other atmospheres. On its own, insulating just the bottom wasn't enough, so I moved to insulating the rest of the atmosphere. I started by measuring the face and accounting for the thickness of the insulation itself, just to make sure everything would line up once everything was in place. Once I had those dimensions, I cut the front panel and taped it against the front of the atmosphere. From there, I moved on to the two sides. These were a little more involved because I had to account for the heat exchanger and leave enough space to properly encase it with the insulation. On the side where the atmosphere connectors come through, I used a 4-inch hole saw to cut clean openings so that those connections could pass through without any gaps. Once those pieces were cut, I was able to press fit them into place and hold everything together temporarily with duct tape. After the sides were on, I moved up to the top of the atmosphere, and just like the sides, I cut the openings for the connectors there as well so that the insulation could sit flush without blocking anything. The last piece was the back of the atmosphere. I added the back panel, and at the bottom, where the heat exchanger inlet and outlet lines pass through, I added smaller pieces of insulation there to close off the remaining open space. Once everything was in place, I went back and covered the seams where the insulation panels met, using duct tape to tighten things up a little bit more. It's not airtight and it's not meant to be permanent, but it does a pretty good job of wrapping up the atmosphere and limiting that unnecessary heat exchange. The build itself was pretty straightforward. Nothing fancy, no major compromises, just careful measuring and fitting so that the insulation did what it needed to do. At that point, the setup was pretty much complete, and the only thing left to do was to let the system run and see how it all responded. By the next day, the insulated atmosphere wasn't any cooler, and the average humidity readings were similar. But what did change was how the system handled moving air. Instead of moisture lingering on the glass, it was being cleared more consistently. Condensation was forming and being processed continuously rather than building up and stalling in place. What this suggests is that the insulation isn't lowering temperatures inside the atmosphere, but it is reducing energy loss into the room. This allows the internal temperature gradients to stay intact longer, even if the sensor readings don't change dramatically. Warm, humid air from the lake and lakeshore biomes rise into the atmosphere where it cools and condenses. With insulation in place, that process happens faster. The convection loop tightens, almost like speeding up a conveyor belt, pulling humid air out and replacing it with cooler air more efficiently. Another factor here is the glass itself. The atmosphere is separated from the heat exchanger by relatively thick glass, which limits how quickly temperatures can transfer across that boundary. So even if the insulation helps preserve internal gradients, the rate at which cold can enter the atmosphere is still constrained. That helps explain why insulation alone doesn't dramatically change temperature, but it still improves how tightly the system operates. After seeing that result, I insulated the atmosphere above the grassland biome as well. This is the most humid space in the system, largely because dense vegetation presses directly against the glass and traps warm, moist air inside the foliage. And so once the atmosphere was insulated, the effect was even clearer. The humidity on the glass in the grassland biome is now effectively gone. There are occasional small patches that appear, but each day they shrink and clear more quickly than before. What's happening is that the stronger convection current is now sweeping humid air out of the dense vegetation instead of letting it stagnate. Pockets of warm, moist air that used to linger are getting pulled upward and processed by the atmosphere. Numerically, the humidity in the grassland biome has dropped from around 80% to roughly 60% in the mornings, rising into the mid-60s as the light warms the system. That fluctuation is expected, but the baseline has clearly shifted downward. Because the grassland and lakeshore biomes are connected, this change didn't stay isolated. The lakeshore humidity has dropped even further, now sitting below 50%, even though the temperatures in both biomes remain warm. That's an important distinction. The system is still warm, but the moisture load is lower, and that means that I now have a much wider range of control over humidity without needing to change the temperature. At this stage, insulation still isn't a standalone solution, but it's no longer a subtle effect either. It's a lever. Once the rest of the atmosphere design is functioning properly, insulation allows the system to move air and moisture decisively instead of sluggishly. There's still work to do. These atmospheres need to be fully refurbished so the cloud mechanism and rain systems are reliable again. That's the next focus, getting all 4 atmospheres operating with their full design intent. And so once the atmospheres are efficient, insulated, and producing constant rain, that's when the next layer comes into play. Adding heat exchangers directly to each biome will allow me to tune temperatures independently from humidity. That's what opens the door to real climate control. Warm biomes that stay dry, cooler biomes that stay humid, and eventually seasonal shifts across the entire system. Much further down the line, I'll be building completely new atmosphere designs using thinner glass, so that the cold generated by the heat exchangers can move into the system more efficiently. Those redesigned atmospheres will eventually sit over the lake and seagrass biomes, which currently share air with their neighbors. But for now, this test did exactly what it needed to do. It clarified how the system behaves, revealed where efficiency actually comes from, and showed that small informed changes can unlock much larger control. Before I wrap this up, I want to thank everyone who supports this project on Patreon. Each biome in the system is supported by people who choose to support their favorite part of the ecosystem, and their names are physically part of the build. I 3D print plaques with their names and place them on the cabinet doors beneath each biome. That support makes experiments like this possible, and it lets me move carefully instead of rushing decisions. If you'd like to support the project and become part of this story, you can do that by sponsoring a biome on Patreon with the link below.